Okay, for electronegativity, we can express in terms of numerical scale. So, for instance, from 0 to 4. So, from left to right of the periodic table, the electronegativity will increase. So, when we compare electropositive atom and also electronegative atom, electropositive atom is the one having low electronegativity, and it gives up electron to form cation. So, that means the atom lose the electron to form positively charged. Okay, so that's why it have the positive oxidation number. So the opposite is for electronegative atom. That means it attract electron to itself, so it take more negative things to it. Okay, it takes more negative charge to it. So because it accept more electron, and when it has the net more negative charge, so it form an ion. So that's why it is indicated by negative oxidation number. So just very easy, right? Electronegative atom has negative oxidation number. Electropositive atom has low electronegativity, and also it can readily lose its electron to form cation. And that's it for electronegativity. So here is the electronegativity and periodic table. So based on my explanation just now, you can already see that the element on this right side has the highest electronegativity, okay, from left to the right or from bottom to the top. So that means the top and the right side of the table has the highest electronegativity, okay. Meanwhile, from the lowest electronegativity is from this bottom right hand side corner, okay. So it's easy, right? Okay, so this arrow is showing the direction of highest electronegativity. So that means from left to the right and from bottom to the top. Okay, let's have a look into the next slide on metals, metalloids, and non-metals. So we focus with the reactive metals first, okay? So reactive metals, or also known as metals, is elements with low ionization energy and also little to no electron affinity. So that means it is usually electropositive because it easily give up the electrons, right? That means it loses the electrons in order to form cation. So you have to remember that reactive metals belong to the alkali metals in group 1A and 2A, except for hydrogen, because we know that element hydrogen is not in solid phase. So what is more important, you have to remember that alkali and alkali metals belongs to group 1A and also group 2A, okay? So this is what you have to remember. Okay, for reactive nonmetals, or shortly nonmetals, it is actually the elements with higher ionization energy, and it is also it has the tendency to accept electrons and form an ion. So it is usually for elements in group 6A and 7A. So these elements are actually non-metallic. So for instance, Cl, Fl, Br, sulfur, oxygen, and so on and so forth. Okay, so these groups are non-metals and having the tendency to accept electrons and become negatively charged. Okay, so next is on metalloids. So metalloids is actually the elements that can behave either metal or non-metal because it has intermediate electronegativity. So it is not too strong, right? Because it is in the middle. And it is usually found for group 3A, 4A, and 5A. And the last category is, of course, noble gas. It is also considered as non-metals. So this is actually the element which is very stable and inert because it has the complete valence, okay, S2 and P6 configuration, so it is complete. And it has no electron affinity because it's already stable, and therefore it is non-reactive, and it has no electronegativity. So group 8A is exceptional because it is under very stable condition. And for instance, argon, right? So argon usually, sometimes you use argon to purge oxygen if you like to carry out the synthesis under the condition without oxygen. Okay, so you can find out what is the condition of synthesis that require no oxygen presence, and why argon is used in order to have such inert condition. Okay, so I think now we can go through some example. Okay, let's try this problem 1. So the most abundant isotopes of iron are ferrum, and there are 1, 2, 3, 4 isotopes of ferrum with their so this is their percentage. So that means we have 91%, 91.7% for ferrum with isotope 56, and 5, and so on and so forth. Okay. So for 56 here, the atomic mass is 55.934 AMU. Okay, so here are the questions that need to be solved. So I would like you to try. And the first one is find the average atomic mass of ferrum. Okay, so find the average atomic mass of ferrum. So what you can do is actually take the first one, for instance, 55.934 AMU, right? So this is the atomic mass of the ferrum for 56 Fe. So, and the existence of this isotope is 91.754%. So you multiply this, okay? And then, so you get the first one. Similarly, you take the second one also and multiply with the existence of that isotopes, okay? So maybe I can sketch here in the slide. So the existence of those isotopes, you should multiply with the atomic mass of each isotope, and then you get the answer, right? So you repeat this all together. Okay, you repeat this for all the isotopes, and you take the summation value here. Okay, so let's do this. Okay, when you already sum up of all this value, just make sure that you divide by 100, because the total of existence of this isotope is of course 100. So divide the summation that you get here with 100. Okay, one moment. Okay, so please try to calculate on your own. Okay, and then post that in the e-learning. The one that I have explained to you just now, of course, is for question problems 1A. Okay, so for this one. Okay, then what should be the relative atomic mass of iron for B? Okay, for A we have completed. For B, please try to do this. Okay, for C, how many atoms are there in 55.84? So 55.84 is actually the atomic mass of the iron, right? So if you still remember last time, for and this is actually equivalent to 1 mole of ferrum. So 1 mole of ferrum, or 1 mole of any element, always having the constant value of atom, which is 6.023 times 10 to the power of 23 atoms. And then for D, how many are there in 1 gram of ferrum? So that means if you have 1 mole is about 55, then for 55 grams, so you just do some mathematics here in order to calculate for D. Okay, and then what are the mass in grams of 1 atom of ferrum? So you can also calculate that, and also F. Okay, so please try this on your own. I will see, or I will check your answer later, and maybe I will share also the answer with you. Okay, then next is on example problem 2. So here are the question. Okay, the question is on alloy, which is nickel and copper. And here we have 100 gram of nickel and copper alloy. So nickel is 25% in weight, and copper is 75% in weight. That means we have 75 gram of copper and 25 gram of nickel. So what are percentage of copper and nickel atoms in this alloy? So can you try this? So if you refer to here, the atomic number for nickel is 58.69, and for copper we have 63.55. Okay, so let's take this value into your calculation, 58.69 and also 63.55. So I have written the atomic mass for nickel and copper for you, so you should do the same. Then for this, we know that nickel is 25 gram. Okay, for 25 gram, how many moles of nickel in 25 gram, and how many moles of copper in 75 gram? So you can calculate using the atomic mass which is given to you. Then you can, after you get the mole value for copper and nickel, you can get the percentage, and then after that you can get the atoms in this percentage. Okay, so please post your answer in the e-learning. Okay, easy, right? So after you calculate the mole for copper, mole for nickel, and then you get the total, and then get the percentage of each atom. Okay, when you complete with problem 2, let's have a look on problem 3. So it's actually between a compound having nickel and aluminium. Okay, so nickel and aluminium has X and Y here. So the same methods applies in order to solve for problem 3. You have to calculate the percentage. So as I said, it is you can refer to problem 2. Okay, so then you already know that first you need to find the atomic mass. Okay, for nickel and aluminium. For nickel, you already have here for 58.69, and for aluminium, we can look from periodic table. So aluminium is having 26.98. Okay, so we write it down there. Then convert this into mole. Okay, calculate the mole when you have 42.04. Let's say weight percent, you have total of 100 gram, right? So take this 42.04 with the atomic mass of nickel of 58.69 and get the mole for nickel. Similarly, you apply the same way in order to calculate the mole for aluminium. Then get the total mole for nickel and aluminium. Okay, and then get the percentage or fraction in order to give the simplest formula of this nickel aluminide. So I have summarized what need to be calculated here. So please try do this on your own. Okay, so it's not so difficult, and I think you can try first. Okay, so I hope you got the answer for example problem 3. So please post that in the e-learning. I'll provide the links later. So thank you very much for your attention, and we'll continue in the next video for the next lecture. Thank you.